Brilliant. Hi, we're going to start. Great. Well, greetings all. Thank you for coming to this talk by Dr. Andrew Boswell. I'm going to read this to make sure I get it right. I'm Mike Bloomfield. I'm the Secretary of the South East region of the RSC Analytical Community. And this is a combined physical and online talk. There's more people registered online than there are present here, so it's actually quite a large event. So, oh yeah, and it's a joint event. It's a joint event organised between CERAC, the marketing group, and the Kent and Bristol and West local communities. So thank you very much for those guys for joining us on this event. It'll be recorded and available on Zoom in due course. The talk should last approximately 45 minutes with 10 to 15 minutes questions at the end. There'll be a networking session afterwards, so if you can stay, please join us after that. Please can all questions be directed to the end, where Steve Barton, our treasurer, will collate any questions that come through from our online attendees. Finally, the practical bits for Burlington House. If you want the toilets, if you haven't found them already, they're at the bottom of the staircase. On the left-hand side, go to the end of the corridor, and then the toilets are on the left. There's no fire alarm planned for today, so if the alarm goes off, it's genuine, in which case, please exit where you came in and go out onto the courtyard. If you can't do that, please go out through the Geological Society, which is next door, and assemble on the pavement. So that's the end of that. Now the more interesting bit, I'll definitely read this, and this is the background for Andy. Dr. Andy Boswell is a very good friend of mine, and we both studied chemistry at Imperial College. We both had an interest in foreign travel, and Andy organised an interrail trip around Europe. But I do seem to remember during that, we got turfed off a bench in Copenhagen after visiting the Carlsberg Brewery with lots of free beer. So all very naughty, but a good fun event. Anyhow, Andy graduated with a first at Imperial College, and then went on to complete a DPhil at Oxford University in molecular and structural biology and of binding in proteins, using the then new field of NMR, nuclear magnetic resonance, which I think we all know. In the 80s and 90s, he expanded his interest to software engineering and computational modelling. Very large-scale integrated circuits, which was a new field then. This continued with a career-long engagement in complex systems analysis and the interpretation of scientific evidence. From 1995 to 2006, he managed and led the high-performance computing service at the University of East Anglia, which he designed and developed from initial conception. Several incarnations later, the service continues to operate in operation today, providing vital computing services, campus-wide scientific research across multiple disciplines. Almost finished. This scientific modelling included climate science investigation, and this, of course, has led to the research for this presentation. He's now an environmental consultant and expert analyst, working at the intersection of science, policy, and law, and particularly relating to ecology and climate change. Wow. Without further ado, I'll now hand over to Dr. Andy Boswell.
Right. Thank you very much, Mike, and thanks to the Royal Society of Chemistry and CERAC and Bristol and Kent and the marketing group for organising this lecture, and everybody else who's been involved in organising it. So I'll just go straight into the Rogues Gallery. Back then in 1976, when Mike and myself were at Imperial College together, and in that picture you'll see Mike is there. And Professor Dennis Evans, I'm going to dedicate this lecture to Professor Dennis Evans, and I'll talk a little bit about him on the next slide. He was one of our lecturers, and myself there. So Dennis Evans was an amazing ingenious experimental scientist, and also a theoretician, actually. Did a lot of work on NMR. I remember the Evans effect being talked about when I was at Oxford later on. And infrared spectroscopy. And the link here today for Mike and myself is that a lot of the effects we're studying on climate science are basically effects in the infrared and absorption of infrared. So I'm going to just talk a little bit about that to give it a link back to our days at Imperial College. And looking forward to the talk, that will be that bit. And through that, I'm also going to draw out molecules and effects and impacts of interest. And what I mean by this is actually not molecules and impacts of interest in terms of climate science itself, but more in terms of carbon capture and storage, because that's the subject for tonight's talk. And then move on to carbon capture and storage. And at that point, I'm going to introduce what I call the 4 uncertainties in the full life cycle of greenhouse gas assessments. And that's really the sort of center of the work scientifically. And then I'll move on to the science and how the science is or is not being represented in policy, and also actually in the planning system, because that's where I've done quite a lot of work, and the UK's methane blind spot in that respect. So first of all, the greenhouse gas effect and climate science. This is a very well-known chart from 2009, the paper by Kevin Trenberth, and it basically, I've managed to switch the presentation off. I'm not sure if you can help me at the back of the room. Oh, that's it. Incoming sunlight there, which is largely, of course, the visible spectrum and a bit outside it. The incoming solar radiation, the yellow band, and then outgoing radiation from the Earth. And in a stable climate, typically what we had for about 10,000 years before the Industrial Revolution, that outgoing infrared radiation would be the same as the incoming radiation. But we know that now that's being perturbed by greenhouse gases in the environment. And what we're getting is a little bit more back radiation. Of course, there always was back radiation all the way through that 10,000 years and way back millions of years. But the perturbation now is we're just getting a little bit more of that, and that's the heating effect. And it's a very, very precise effect, like some of these effects you have in science, difference between 2 big numbers. And that's the incoming radiation and the outgoing there. And if you see, there's just 0.6 watts per square meters at the surface of the Earth between those two. And that effect is the greenhouse effect. And I want to show another slide which basically maps out those two. So here we have the black line is the incoming radiation, and the red line is the outgoing. And you just see that small difference. And in 2009, it was that bar there, the 0.6. Climate scientist Leon Simons, who drew this graph, has called this the most important graph in the world. And I should say this is all captured by satellites now and is also very accurate. We'll also talk about satellites later on in a different context. I noticed the exhibition outside as well had a bit on satellites. But now that 0.6 as it was in 2009 is now up at about 1.4 watts per square meter. And this is actually causing an acceleration of temperatures. And it's still being debated in the climate science community. It'll probably go on being debated for a number of years. But quite recently, there's been a number of papers, and one last month actually, which has said there's effectively nearly a doubling of that between the period from 1960 going to 2010. It's more or less constant rate of increase of temperature. And then over the last 15, 16 years, it's been accelerating, almost double the rate if you draw the straight line between that. So that's where we're at with quite a serious problem with the climate crisis. Going back to those greenhouse gases, just blowing up that bit from the previous slide, I just want to highlight the molecules which are of interest for carbon capture. There's lots of other greenhouse gases there, but the molecules of interest tonight are methane and carbon dioxide. And they have very different characteristics in terms of how their life in the atmosphere. Carbon dioxide's basically long-living, will stay there for hundreds of years, and a lot of the policy to date has been directed to carbon dioxide and to stabilizing long-term temperatures. But methane has a very short-term impact, very short, intense heating. And this slide just shows a pulse of methane in the blue and what's called radiative forcing. The radiative forcing is effectively what's on those previous slides, the difference in the radiation. And when methane gets engaged in the atmosphere, immediately you get an effect on the temperature, and then that declines very rapidly. The half-life's about 8 years of methane in the atmosphere, which you can see on that slide. The heating effect comes a little bit later, just through how the climate system works, but the pulse of radiation in 2010, in this example, will give you a peak of heating about 10 years later, and then it declines over about the next 20 years. So you're talking about a 30-odd year effect from methane rather than the hundreds of years you get with carbon dioxide. So those are molecules of interest, effect of interest, and the real-world impacts. So now let's look at carbon capture and storage. Now, I'm going to very tightly refine down what I'm going to talk about on carbon capture and storage. There's lots of varieties of carbon capture and storage, but I'm specifically going to talk about carbon capture and storage based on natural gas. And one of the reasons is that that's the majority of the government policy, is to invest in natural gas-based carbon capture and storage. That's either for blue hydrogen or for gas-fired power. But there are a lot of other applications I'm not going to talk about tonight. I'm also just going to focus on greenhouse gas cycles, greenhouse gas life cycles, and not about other impacts. I might mention some just slightly. So for climate policy, and looking at the greenhouse gas life cycles, is gas CCS, gas-fired power stations with CCS, a climate benefit or disbenefit? And what I'm going to postulate to start with is that can only be answered with a full knowledge of the effects and impacts. And I'm going to express that slightly in legal terms, partly because that's where I've operated bringing science, but it also sort of makes sense from a scientific point of view, that if you want to reasonably foreseeably look forward to what these impacts might be, then you have known knowns, and I'll talk about some known knowns, and that's the starting place for everything we do, and known unknowns. In terms of the UK legal system, there's basically a concept of reasonably foreseeable worst-case scenarios in terms of doing environmental impact assessments. And that captures that sort of known knowns, the known unknowns. But of course, the legal system, quite rightly actually, doesn't want to deal with unknown unknowns because you can't resolve that really. Though, obviously you can do risk approaches and things like that, but we're not getting into risk analysis tonight. But that's where we're constrained in the legal system, and to a certain extent, I think also in policy, because policy is also part of the legal system ultimately and can be challenged. So it needs to be clear on what it's known and what the known unknowns are. And we need to find ways to get some sort of understanding of that, a full knowledge, understanding of the reasonably worst case. And looking at the UK policy and planning, both policy and the planning system, and full life cycle assessments, what I will say at the outset is, and my experience has been that what we're seeing is best case assumptions, so not reasonably worst case scenarios, unrealistic assumptions, which is sort of worse than best case because it's unrealistic, material issues being involved, and the methane effect I've talked about is one of those, and no uncertainty testing. So that's really the framework I'm going to develop out now. And I'm going to start by talking about four uncertainties, but first of all, just one more bit of sort of definitional stuff, if you like, what dispatchable means in policy. There we have a gas-fired power station, maybe with or without CCS. And dispatchable means that in the energy system, that will be brought in when renewables won't deliver. I mean, in the past, they're there for full baseload, but we're moving beyond that now with the extent of renewables we've got. So now gas-fired power, either abated with CCS or unabated, is brought in when renewables aren't delivering. Not enough wind out there in the North Sea, cold days, and so on in winter. That's dispatchable. And that's a useful definition to know. As we go on, I'm going to talk about the four uncertainties now. So one of them is you've got that gas-fired plant, you've put carbon capture storage on it. How do you get rid of the carbon dioxide? That's transport and storage. And I'm not going to say too much about that, but essentially in the UK, it's taking it out to the North Sea or into Liverpool Bay and burying under the sea. I mean, it can be buried under land, but not in the UK example. The second uncertainty is that the CO2 capture rate. Are we going to achieve what is being put forward as best technology? And then the UK gas supply. Now, this is where it gets quite complicated, but the UK gas supply at the moment, you probably know because there's been a lot of discussion about it in the media these last few weeks, but the UK gas supply, quite a lot of it's supplied by the UK continental shelf at the moment, but that's declining. There's pipeline from Norway, which I haven't shown, but you can imagine that coming in from the east there. And there's another component, which is LNG, which can come from anywhere in the world. And we actually, in the 2010s, we imported quite a lot from Qatar, which LNG is now defunct for a while. But increasing the last few years, we have been importing it from the US, and that's increasing. And I'm going to postulate that that is very likely to keep on increasing for various reasons. And then the emission intensity. So effectively, you take all those different supplies and you look at the emission intensities, and I mean the greenhouse gases which are emitted for 1 kilogram of natural gas turning up at your power station in the UK, how much greenhouse gases have been emitted all along the supply chain. And there's a lot actually in terms of the fracking. We'll look at satellite imaging of fracking sites, and there's a lot along the LNG shipping. There's more when it gets regasified. It's liquefied so to be exported, LNG export facilities. It's regasified in the UK, some in the national transmission system before it ever gets to being combusted. Okay, I'm just going to say a little bit about the storage side of CO2. Just one slide on this. And The only bit, because I'm talking about greenhouse gases and tending to look greenhouse gases on an installation, I'm not going to talk about the issues with the undersea storage, geological storage, except to say that there are serious issues with that and risks. And there's known examples, two in Norway, one where they started putting CO2 into a geological strata and then found that the plume had moved much further up. It was sort of going in, I'm not exactly sure, but thousands of meters underneath. It moved up in a way which is unexpected, much closer to the surface. And if that had been a geological strata which was open to the atmosphere, it then would have leaked. That's one example. Another one also in Norway where the geological survey said there's something like about 18 years of CO2 storage in this cavern. They started pumping it down, and after about 18 months, the equipment started getting sort of very hot, and they couldn't pump it down any further, pressure building up. And basically, it could only take 18 months. So there's all those sort of issues, which might mean that the storage doesn't actually work as we might hope. But I'm only going to concentrate really on the pipeline bit, and there's a built-in assumption that typically the pipeline and all the onshore infrastructure and so on is going to be unavailable between 5 and 6.5% of the time. I'm basically not going to sort of challenge that assumption because it's a difficult assumption to challenge. We don't know till it actually happens. But that's a sort of known unknown going forward. But so that's covered the transport and storage, the first of those uncertainties. Now we get to the real world carbon capture rate. And this is from a graph from 2023, but they've just confirmed it actually last month, from IEFA, which is the Institute of Economic and Financial Analysis, Energy Economics and Financial Analysis. And they do a lot on carbon capture and storage. And I'm just going to highlight this, this is for post-combustion CO2, which is what we're talking about with gas-fired power stations in the UK. It's actually coal plants in the US historically, because we haven't, worldwide, there are actually no gas-fired power stations of CCS yet. And the policy, this red line is 95%, and that typically actually is what the industry is claiming now. But on some in the UK, they have claimed 90%. But the policy and what we're seeing in the planning system is 90 to 95%. And there's a big gap there between what's actually being delivered out there in real world systems to date to what the policy is being built upon. So now I want to give you some of the sort of numerical work I do in terms of challenging this both as policy and in the legal system. And this is for a gas-fired power station currently going through the planning system at the moment. It's about halfway through its planning examination. And I'm first of all going to talk about that CO2 carbon capture rate and look at the known knowns and the known unknowns in that. So this is what you might call an indicative sensitivity test. I'm not claiming this is going to give any of the right answers as such, but what it does is give a sense of the uncertainty, and this is what is not currently being done, either as a policy basis or as a planning basis. So I'm going to start off with the known, and this is all in tons of CO2 equivalents, which is greenhouse gases. But this is absolutely a known, because this is the combustion emissions. So this is the emissions coming out of the stack, and this is when it's unabated. So if we know how many megawatts the plant's going to be, and this one is actually 2,800 megawatts or 2.8 gigawatts of thermal energy, we know exactly how much CO2 we need to create that, the calorific value of it and so on, and we know exactly how many greenhouse gases will be, because it's just the CO2 coming out of the mass balance equation. So that's a known. The next figure down, the 5%, is that transport and storage one I was showing you, which I'm saying I'm not contesting in tonight's talk. But after that, that basically shows that if the transport and storage is unavailable, already 7 million tonnes of CO2 will be vented to the atmosphere. We're starting off from the combustion as 146 million tonnes of CO2, incidentally. So then you get the remaining emissions that you can capture. This is still sort of unabated, if you like, but we've accounted for the bit we're venting. And then at 95, and actually the figure which came out of the environmental impact assessment was this one with rather a lot of other numbers after it. It's effectively 95%. And here I've put 70%. Now you may think, why have I put 70%? Good question. Well, the reason I've put 70% is that these power plants, gas-fired with CCS, get subsidies from the government. And one in Teesside has already got £8-9 billion of subsidies awarded to it. And the basis of what they call the dispatchable power agreement for that plant says that it will be given these subsidies as long as the capture rate, as long as it's capturing at a rate of 70% or more. So legally, they're saying, well, we're going to pay you money for this if you capture 70%. So it's entirely reasonable to say, well, that could be the reasonable worst case for the thing to operate legally, although the environmental impact assessment is saying 95%. And then when you do the numbers, basically on this one here, you get 6 times as much because it's sort of 5% rather than 30% saved, so to speak. And you see that's quite a multiplier. So the figure going ahead into the environmental impact assessment for the combustion emissions once you've done the capture is 6 million tonnes of CO2. But it could be possibly much higher than that, even 41 million tonnes, and still operate legally. That's everything on the capture rates. And I want to come on to these two, which you sort of have to do together a bit, the upstream emissions. I mean, I'll refer to them also as just upstream emissions, and effectively say that the upstream emissions are a function of the supply variation and the supply intensity. So the supply variation, I mean all the issues like, is it Norwegian gas? Is it UK gas? Is it LNG coming across the Atlantic, or possibly coming in the past from Qatar or whatever? And then the supply intensity is the greenhouse gas emissions along those different supply chains. So first of all, I want to say, if we forget about capturing the carbon for a moment, and we look at the total emissions in the whole process, before, not including the storage bit, but up to that point, up to combustion, the total emissions up to combustion, without the capture, effectively 2/3, if you're using LNG, 2/3 of the emissions are before you can get to the UK. And 1/3 is the combustion emissions. Now, this comes out of satellite work I'm going to introduce, and it comes out of scientific papers, including a recent one about 18 months ago. I want to put a couple of other figures on, and this is sort of looking forward to what I'm going to introduce now, so you've got a bit of an idea of where I'm going with sort of outline numbers. If you then do the capture, yes, you reduce this bit down to sort of 6% of the total, but the overall, out of the overall process, 94% are the upstream emissions. So you can see the upstream emissions are very, very dominant. And a lot of those are methane. The CO2 in the upstream emissions as well, as we'll see, but a lot of them are methane, and that's giving rise to that short-term impact and short-term temperature rises. So I now want to sort of drill into this. Upstream emissions are a function of supply variation, supply intensity, and lay out some of the sort of, if you like, parameters of my thinking, and then put some numbers on it. So I'm going to say, as always, there's known knowns, and we always start with the known knowns. And then there's known unknowns, and those may be uncertainties, genuine uncertainties, or they may be just effectively sort of wrong data, or in this case, out-of-date data. And one thing I'm going to say is a lot of how the UK base their policy and also planning decisions is out-of-date data. And this is also a black box. What the UK government come up with one number, effectively, is called an emission factor. And they basically say if you apply that to the amount of CO2, if you apply that to the amount of natural gas, rather, then that will give you the upstream emissions, CO2 and methane all combined. It's not a bad principle to have an emission factor, but the derivation of it is a black box. And in terms of policy and in terms of the planning system, the public, there is basically a principle that the public should be able to engage in all the environmental issues and question them. And actually, we're not being able to do that at the moment, but I've unpacked it effectively quite a lot in my work. So we don't really know what the output is. And just to go through that, the known, of course, is the gas volume like we had on the other example, and also historic gas supply. We know something about the historic gas supply, which may give us some clues. The future UK gas supply is a sort of known unknown. We know it's going to vary, and we've got some idea of how it might vary, actually, but we don't know actually exactly what it's going to be. And then where there's data which is out of date or is just sort of basically not correct. Recent satellite data on the emission leaks from fracking and along the supply chains has not been taken into account. Recent scientific studies of the full life cycle greenhouse gas emissions not taken into account. And the near-term methane impacts are effectively attenuated, effectively zeroed. So I'm now going to move forward to unpack some of those. And this is from NESO, the National Energy System Operator. And it's a chart of the future UK gas supply. And this is 2024, which is really when the chart sort of started, or sorry, where the chart was drawn. And we know at that point that there's that amount of LNG in the system, because that's data you can look up, and that data is all there and everything. NESO were trying to project out what would happen to 2050, and because they don't know exactly, I'll start that again. Well, I should say, first of all, this is UK gas, so that's from our continental shelf. And you see that declining out to 2050, as we know it will. Even if we do short term, even if it's brought back in short term, it will still decline very rapidly. Norwegian gas, ditto, our pipeline from Norway, the blue. And then there's also this pink streak here, which is continental gas, brought in pipelines from Holland and Belgium. Now, actually, after the Ukraine crisis, that just went to zero, because Europe wanted all the gas for itself. In fact, we started exporting more to Europe at that point. So that the continental one has basically dried up and is unlikely to come back in real terms. So what NESO were doing was they were trying to project that, and they said, well, we might still have continental gas coming back in somehow. And they put this block here, which is generic imports. Now, the thing about generic imports, they say quite clearly it's LNG or continental pipeline imports. So the continental pipeline imports have gone to zero for the moment. Looking out into the future, that isn't likely to come back. So this block effectively is LNG. And we can see how it crystallized in 2024. It was already all LNG there. So that's the sort of projection going out into the future. And at 2040, you see that component is 3.4 times as much as it was in 2024. Now, this is also a static picture. This is just a projection of annual gas supply going out to 2050. But you also have to look at what happens in the market and where a dispatchable power station, and remember these things, the gas-fired power of CCS is only being brought in as a dispatchable supply. That's the policy. In the market, this block is dynamic and it's the marginal end of the market. So essentially, the UK and Norwegian gas will carry on supplying domestic and industry what's left. There will be some gas-fired power will go on. We'll talk a bit about that later on. But that is going to be supplied when you get a weather situation that you need to bring in dispatchable power in the future. That's all going to be supplied off the market through buying LNG in the marginal supply of the market. LNG is the gas supply which can respond most rapidly to the market situation, short supply. And they trade on globally and everything on that. We'll come back to that. So now I want to look at the emission intensities, the emission intensity side, and look at where LNG is coming from, increasing the UK. I think 78% of the LNG imported to the UK was from the US last year. And the first thing to say is that the UK government emission intensities, and that what I call the emission factor, is based on pre-2015 data. This is 2022 data of the Permian Basin in a large area, actually overlapping New Mexico, Texas, and Mexico there. And this is actually 400 kilometre by 700 kilometre area. And they've mapped out data from many, many plumes. There's also a study which mapped out data from over 1 million sources, actually, of satellite information. But this was methane sat in 2022. And the sort of headline point here is that the US inventories, which the UK one might be indirectly based on, is also completely out of line with what the satellite information is saying. And the US government is saying there's 1 to 1.2% leakage. What that means, for every kilogram of methane or natural gas you extract, there's going to be 10 to 12 grams of methane released to the atmosphere. That's what that percentage means. Methane sat was getting 2.8%. And that's very, it's also a long tail distribution incidentally, and sometimes it's up to 13% or something like that. So now I want to come on to peer-reviewed literature. And one of the things I say is you've got both the satellite data, but you've also got first principles scientific papers. And this one is from Professor Robert Howe, a very recent one. There's quite a few of these papers. And he's a methane researcher, long-term methane researcher, actually. And he was responsible, actually, for the Biden administration pausing LNG making new LNG export facilities. They paused the planning on that in the Biden administration on the basis of Bob Harris' work. And he said that ending the LNG should be a global priority, a statement I'd actually agree with. I don't want you to look at the numbers on this one. I'll highlight the numbers where I do, because they're very confusing. But I just wanted to actually reproduce something directly out of his paper. And there's a couple of points I want to make. One is, right up here, this says United States to UK. And one of the things which is really helpful with the Bob Harris study is that he actually mapped out a US to UK half with the LNG tankers exactly working out the emissions. He also did the US to Shanghai, which of course was higher because it was a much longer LNG journey. The other thing is he did it over 4 tankers, and you get various variations, but I've chosen this steam turbine powered LNG because that's the way the industry is going with the LNG tankers. So that's more plausible for a forward-looking analysis. And the other thing I want to say, it is just full life cycle. So it goes all the way from the upstream, midstream, liquefaction, emissions from the tanker during the journey, as on the previous slide, a transmission system in the UK, regasifying the gas, and then the final combustion. He puts the burning in there as well, which of course is the known for us getting our numbers out. And doing that, I just put a summary here where we've got the combustions the same on both lines, but I'll need to flick it on. That one there includes the short-term methane impact. This one doesn't. And what you can see, what we're doing here is not creating a proper emission factor. We're creating a factor of emissions or ratio of emission factors. But what we're effectively saying is what's the upstream rate of combustion emissions? And then the combustion emissions are known. So it's quite a useful way of doing it. And it's 1.6 where you include the methane, and 0.8-ish, a bit over nearly 0.9, when you attenuate the methane. So nearly double effect for not including that short-term methane. Or when you do include the short-term methane impacts, you get double the number-ish. This is the UK government emission factor as of 2025 tables. It's about a tenth of that one. So this is where the numbers sort of highlight the issues I've been talking about the inventories the governments use being out of date with latest science and satellite evidence on. And the Harris paper is based on the similar satellite evidence to the one I showed. I now just want to take that forward. This is back to the current gas-fired power station going through planning system. You might, another indicative sensitivity test, you might recognise that 146 million tonnes of CO2 figure was where we started on the other one. So it's the same known. And now we're just applying those different ratios, the ratio of emission factor to it. This also includes those emissions vented, loss of storage, and other things. It also includes the captured, the emissions after you've done the capture, the combustion emissions, at 95% on this one. And what you see is the upstream emissions are actually 24 million. But the total's 38 when you include the other stuff. So this is all like the full life cycle, if you like, is 38 million. And when you attenuate the methane, but you do the upstream analysis, on of the impacts otherwise without including the short-term methane. It's it's 144 million tonnes, and then 263 including the short-term methane. So you can see the scale of impacts we're talking about. And this just brings us back to that 94% figure I had on the slide way back. That's where that's from. This is showing those same three scenarios, the sort of government, industry, government policy and planning, the upper bound without the methane and the upper bound when you include the short-term methane. And the scope 3 WT emissions, that's the upstream emissions, though they're 64%, or 63% rather, in the government one. So they're still saying, yes, the upstream emissions are big. But when you go over here and you include the full impacts, and remember the absolute values have sort of gone up a lot here, you're getting 94% are the upstream emissions. So this is the problem. Now, 4 years ago, it was a different problem. I'm now going to move on. I've sort of covered the four uncertainties and the science. I'm going to move on to the legal and policy area. And just before I do that, I wanted to show this, that this was back in 2022 when I first started looking at a planning examination, planning documents, the environmental impact assessment for one called Net Zero Teesside. That was the only data being put in. The only data was the post-combustion CO2, the scope 1 emissions. They didn't put anything in about the upstream emissions, anything about the leaking, because the storage might not be operating and so on. So moving on to the policy area and the UK's methane blind spot, we've covered the molecules and impacts, and I talked earlier about a full knowledge approach, and you remember that uncertainty between known knowns and known unknowns. Now let's look at how that applies, but it will another slide first, or another one or two slides. I want to sort of outline, this actually is the bit where I will say what all those other types of CCS are. And we've literally just been looking at gas, which is that one. But this is the cost out to 2050 on the advice given to the government from the Committee on Climate Change for something called the 7th Carbon Budget, which actually is going to be set in June. And the gas is about 135 billion of investment, CapEx and OpEx, out to 2050. Now, I'll shoot across the other ones, but there's a point I want to make here. That there's biomass, that's BECCS, biomass or bioenergy with carbon capture storage called BECCS. The carbon accounting of that's all wrong as well, and I could talk for another hour on that, but I won't tonight. And then we've got blue and green hydrogen. Unfortunately, the Committee on Climate Change mixed this lot up, but blue hydrogen, green hydrogen's okay sort of thing. That's where it's made from wind energy and renewable energy. But blue hydrogen's where it's made from natural gas, and that also has all the same upstream emission issue when you produce blue hydrogen. There's direct air capture, which is something really being developed for removing historic emissions in the future, and we may come back to that in discussion. It's potentially quite important, but it's extremely inefficient now because they're trying to pull molecules of CO2 out of the air. Energy from waste and incineration, I don't say much about that, but it's sort of clumped together in industrial emissions. What you'll see is there's much smaller funding for over here. But what the government say in their policy is that, oh, we want to do CCS because we want to capture the emissions from hard to abate sectors from industry. Now that, at one level, that's a reasonable thing to say. But what they don't say is, but all of our investment, or the vast majority of the investment plan for the UK is going into fossil fuel or biomass-based CCS, and that also is part of the problem that effectively there's a greenwash problem there in that. They're not actually being completely honest about what it is in the policy documents. So this is all being done, this is background to what's happening. It's all being done in clusters, and there's 2 clusters which have been given go-ahead already. And like I said, there's the 10 million here in Teesside, and in fact I think I've put the power plant on there. That's net zero Teesside there, but there's also other industrial emitters perhaps coming into there, but they haven't been clearly identified yet. And there's HyNet over here in Liverpool Bay. That's based on a blue hydrogen plant at the centre of the cluster. And then we've got one in Scotland, and Humberside's really bidding to the government to come through on something called Track 2 at the moment. There's one here you may have heard of, which is Peak Cluster, which is in Derbyshire and Staffordshire, and that is decarbonising the cement industry with a pipeline going about 150 miles out to Liverpool Bay, then up to Morecambe Bay, actually. And it's actually the focus of a very controversial campaign at the moment. We did a consultation, and sort of thousands and thousands of people have objected to that. They've objected to the point of the pipeline going near their houses, particularly in the Wirral. Now, carbon capture and storage for cement is an interesting one because it's one of those hard-to-abate sectors. It's possible there could be a case made for it, and obviously the promoters of this are saying they have done that. But there's alternatives to decarbonising cement coming along as well. And I think there is a question, we'll come on later to questions of timing and what gets there first and so on. There is a question of timing, whether these alternatives will come on quickly enough. So I'm sort of agnostic on the principle of that one, but I think the case has still yet to be made conclusively against the alternatives to using carbon capture for it. And there's other clusters. Now I want to come on to the energy system. And obviously I was talking about gas-powered CCS, and that's the main focus of my talk. And what I want to say on this slide, first of all, is that we're seeing a movement from this decade. We're seeing a massive transition from molecules to electrons in the energy system. We're moving from burning molecules of fossil fuels to delivering electrons largely of renewable energy. And this is another report from NESO, actually, to the government, 2024, late 2024, Clean Power 2030 report. And the government adopted all of this, actually, and basically reproduced the report and said it's our policy. And most of it's really good policy, by the way. I really support most of this. So the transition from molecules to electrons, they put 2 pathways in, 2 possible pathways. And one is that one where you basically, I should say, sorry, that in this box, which is what I'm calling the electrons, you're getting this bigger chunk of electron-based energy. And that is based on nuclear, offshore wind, onshore wind, solar, and other renewables. And what's left in that first one is unabated gas, that light grey. If you go to this one, you've also got the sort of blue, dark blue one, gas CCS. So what they're saying there is we could either race to 2030 with a big investment into offshore wind and other renewables. I mean, solar increases there and others as well. And before 2030, we won't need gas CCS in the system. We can keep the lights on without gas CCS, right? But in this one, we're slightly slower on the renewables, and we bring in gas CCS to balance those days when the weather's not very good. Now, I lost my train of thought for a moment. Yeah, what I was going to say is, less so, to be fair to after 2030, they do say we want gas CCS. So this is planning to get to 2030, but they're saying after that, we will need some gas CCS. And the reason for that is to displace the grey bit, and more displace the grey bit with abated gas. And that sounds reasonable as a principle initially till you look at the numbers like we have been doing. So I want to go through that substitution of gas argument. And this is basically the numbers I've been talking about, which are using out-of-date factors, out-of-date science. So yes, that's all an unabated gas plant, that's the combustion emissions, that's the upstream emissions. And you've got some other stuff in there as well. That's what would happen if you put CCS on it at 95% capture rate. Okay, so you get a 72% gain. However, when you do the numbers we've been looking, these are exactly the same numbers, by the way, as on all my previous ones. I've just transmuted them into this graph. That's what the abated system looks like when you do the upstream emissions in that reasonably worst case. And then the gains are much smaller. And one thing it's worth pointing out is this pink bit is the CCS energy policy. This power plant, which I said was a 2.8 gigawatt power plant, it generates about 1.4 gigawatts of electricity. About 43% is lost. The efficiency of going from thermal to electricity. The other 7-ish% is the energy you have to use to power the CCS kit. And in this case, it's actually around about 200 megawatts. So there's a lot of energy going in to power compressors and so on, and all the rest of it in the CCS. So then you get down to, this is if you reduce the capture rate, saying, well, we're probably not going to get 95%, that's the 70% one. You get these reasonably worst cases that you could be up to just gaining somewhere between 13 and 20% or something like that by substituting abated gas for gas in the power system. So I'm going to say in terms of policy, that tackling the lock-in to fossil fuel molecules, whether it's abated or unabated, the issue we know is Dunkelfelt and the dark doldrums in the weather system and the energy system. What he says, we're at this critical juncture. You can see that from what NASA are projecting, that we're displacing molecules very, very rapidly with electrons in the energy system. And these gas CCS projects, the one I'm talking about is actually planned not even to come on stream to 2035 and then run to 2065. So you're talking 40 years out. This thing would still be running in theory. An evidence-based approach is needed to look at this in the round. And one of the key technologies which, as well as abated gas substituting unabated gas, will be long-duration energy storage. Now, at the moment, we've got very little long-duration energy. We do have some. It's like where you've got a reservoir up in Scotland and they pump the water up and then it comes down. That's pumped hydro. Comes down when there's a shortage of energy. Long-duration energy can deliver anything from 8 to 24 hours or even beyond 24 hours into the grid when there's nothing else. Well, there's some stuff up generating energy, but at the margin, you haven't got enough energy going in. You can bring this in, long-duration energy. And what I'd like to propose, really, and the way I see the energy market going, is that if we said the 2010s were the decade where we stopped using coal and we went to renewables somewhat, And we also went to gas as a transition technology during the 2010s. The 2020s is the decade of growth of renewables, electrification. Of course, electrification also in other sectors like EVs and heat pumps and so on, but talking about the energy system itself here. And some storage of battery storage, all those battery storage parks which are coming out now, short-term energy. The 2030s is the decade for long-duration energy storage. Now, realistically, and I've been looking at the projections on this, I don't think it's actually going to cut in enough till 2035. So we have another one of these gaps, deliverability gaps. After 2035, I believe from the projections I've seen that long-duration energy storage will effectively make gas CCS redundant because it will better do what gas CCS is being put there for, the dispatchable power element. Also, can we use electrons better? And this is all the stuff about things like demand-side response. That's a bit like when we used to put the washing machines on in the middle of the night to get the cheaper energy. You know, you match the demand to when the supply is at the peak and so on as much as possible. And there's a lot of work going on that still, actually. System flexibility in the grid, demand reduction is important as well. I believe we have to do demand reduction. So looking at the cost, and this is not just the financial cost, but if you like, the sort of policy cost of CCS, by 2035, that theoretical CCS capacity, which is being talked about, could be being squeezed out by technologies like LDS and also using electrons better and other things we're doing on the grid. And the result of that, you land up with a lot of stranded assets in the system. There's also a fuel cost issue, which I mean, I think with what's happening now is just so relevant. And this is a calculation I did on the fuel costs and projecting sort of LNG costs out into the future and so on, based on the Committee on Climate Change saying we'd have 143 terawatts of gas CCS being generated in 2050. It came out at sort of between 5 billion and 10 billion, with this 7.7 billion as the sort of central sort of most likely band or something. However, you know, that calculation's probably doubled in the last month with what's happening with gas supply and the geopolitical situation. Basically, how much is it going to be next week and next year? That's critical questions. And we could be locking ourselves in also to a system which is going to cost us billions and billions of pounds a year just to keep something going for a very, very small part of the time, actually. These plants are proposed to only be run initially at sort of to about 20% at maximum coming into the system and tailing off as more and more renewables come onto the system. Okay, I know I need to wind up, and I'm sorry if I've gone on. I just would like to talk a bit about how I've engaged in the law in my legal work and the sort of history of that, because my mission has really been tried to take what I'd call evidence-based science into the legal system and challenge some of the ways things are being done. And this is effectively challenging government decisions, ministers' decisions. And it can be on policy, and it can also be on the planning system and things coming through the system. And I looked at this net zero TSOD, and I said it started in 2022, and they had no upstream emissions, as I pointed out earlier. This is where litigation in the planning system, what I call litigation in the planning system, isn't actually going to court, but it's just sort of having a damn good argument with them effectively in the planning system, saying, no, your numbers are not right. That's basically what I do. They introduced upstream emissions. They said, okay, yeah, we think we'd better put the upstream emissions in. But they put them in, of course, at this sort of lowest emission factor, the government emission factor. They also double counted the CO2 capture rate. And if you remember, the CO2 capture rate on the government data was the biggest bar on that one we were looking at. So they put in a massive another lot of capture over the top of it. I spent the rest of the planning examination arguing about that one, and also afterwards, actually, with letters to the minister. They actually denied it. The company denied it 3 times. But when we got to the government decision, the government agreed with me on both points, that upstream emissions but it was their unrealistic case. Upstream emissions had to be included in the environmental impact assessment. They also agreed with me there'd been a double counting error. They then made a decision on that basis, and I legally challenged something called the significance assessment of the decision, and I lost on that because it's actually very difficult to win in the legal system. But the outcome of that was that my legal case profiled CCS much higher in the public domain. There's now a lot more discussion about CCS. It's energised various environmental groups, NGOs, more on it. I'm engaged with a lot of those actors. And also it's having, I would say it's having an impact on the government. They're holding firm to what they're doing. But, they know there's a lot of criticism out there of it. And basically, going forward, that was all essentially, all of that bit, 2022 up to 2025 last year, was basically establishing we need to do upstream emissions. And there's other legal stuff going on, actually, which said when you burn fossil fuels, when you extract fossil fuels, you need to account for burning them downstream, in a famous case called the Finch case. So it was all happening in the legal system the whole time. Now we're sort of moving into another domain, which is, I'd call this full knowledge, and where I came right back at the beginning, the known knowns and the known unknowns. The legal system supports the exploration of both known knowns and known unknowns. But, my case would be that that's currently not being done. And that's where things are sort of going next in principle. It's that reasonable, foreseeable worst case, whether the assumptions have been uncertainty tested, uncertainty sensitivity testing, and so on. So I mentioned campaigners and so on. On the whole, I think what people are saying at the moment, certainly this is what I'm saying, and there's colleagues I work quite closely with, is that we want to see a pause of investment into power CCS, and that's both from gas and bioenergy. But I said I didn't cover the bioenergy tonight, but we could do another lecture on that, and my friend James here also has done a lot on that. So, pausing investment into power CCS and gas and bioenergy. Remove power CCS from the UK climate plans and the energy plans, like the Clean Energy 2030. And the UK climate plans, that's like the 7th carbon budget and the plan which goes with it. Then have an independent review of CCS against the science. And part of that, I think, it is clarifying the strategic prioritisation of industrial CCS, because I'm not saying we don't need some CCS for hard-to-abate sectors, but I am saying we need to make the case for it. And I am saying we need to make the case for that within the whole lot, where we prioritise it with power CCS. And effectively, power CCS, the question I started off with that minute, is it going to do more damage to the climate than it prevents? It's going to do more damage to the climate. So that's why we need to strategically prioritise hard-to-abate sectors in the CCS policy. I just wanted to say one thing, and then I really am going to finish, that we scientists have agency. And we're living in an age of consequences. That graph at the beginning, the Earth energy imbalance graph, we see the Earth energy imbalance going up the last decade, the acceleration. we're going to a point where we are getting security threats, particularly food security, and scientists are predicting even by 2030 we could have serious food security issues, partly due to climate change effects. I won't go into detail of that, but the transformation, I believe, is at the human, community and social level. I've talked a lot of technocratic stuff, because that's an area I happen to sort of like, but I believe that the transformation is in communities coming together and people coming together. And I just want to highlight 3 things. And on the next slide, I've got the QR code again for anybody here, and it's also in the chat on the Zoom, I believe. To a whole list of documents, but I've put in there, look out for the People's Emergency Briefing film. That's coming out on April the 7th. It's based on something called the National Emergency Briefing some of us here went to back in November. And what we're calling for with that is a televised presentation on climate risks and climate security risks going forward. And that would be something like a COVID type presentation, like the ones for COVID, where the government outlined the risks. A national emergency briefing. And the national emergency briefing, which was held in November, was basically done by 10 scientists, 15 minutes each, highlighting food security and all sorts of other issues, including defence and everything, actually, right across the spectrum. Now there's a film made which is going to be shown around the country, premiered April the 7th. I recommend you get to a showing of that. I put in something, the Climate Majority Project, which is a project bringing together people for transformation at this human, community and social level, particularly more about the adaptation, actually, how we adapt in the future to things like food security risks coming up with global heating. And for those more sort of traditionally scientifically oriented scientists for global responsibility who've worked for years and years on issues like this, I put in links to those, and it's all there in the QR code. Thank you very much. I hope there's time for questions. Do you want to navigate the questions, or Stephen?
Yeah, we've just basically open the floor for questions. Anybody any questions?
Thank you. Very, very interesting. I totally agree with you about part of the long-term demand. Thank you very much, Philip Howard, Chair of the Marketing Group. So a great talk. Thank you. And I totally agree with you about the long-term energy storage. There should be a priority demand reduction and things like that. So as a bit of agent provocateur, are you kind of saying that if you have to do CCS, given, and you could do 95% in theory, would coal, which doesn't have all the transmission losses, would actually be better than gas?
Well, I'm not saying that, but because I think we can do it with renewables. I mean, but
if you can't do it, if it's choice at the end of the day, the last thing you do is dispatchable. It has to be something fossil.
But what was interesting with the Howarth study, and this may be where it comes from, is Bob Howarth actually said LNG overall, and this is just even for burning it in the US, he said this. If you burn it unabated in the US, and compare it with coal, LNG is worse because of the upstream emissions. It's got more, there's methane emissions from coal, but they're worse from LNG, largely because of the fracking technique in the Permian Basin. So, coal would give you an edge, but going out, I mean, I'm saying by 2035, long duration energy storage and so on, all these new electron-based techniques, we shouldn't really be thinking of coal or,
I'm saying whether your methodology would actually reveal a difference between coal and gas.
Yeah. And if you read Bob Howarth's papers, he makes that clear, and it's one of the sort of headline points, actually. I think he probably put it to the Biden administration, where they thought, well, we know coal is bad. Yeah, we better sort of, think about pausing the export facilities, which they did for a year. So, I'd use that in that sense, but not as any sense going back to coal. Though, of course, what we're seeing with the Iran crisis is with LNG shortages, we are seeing countries in Asia reverting back to coal. Short term, perhaps, but it is sort of creating huge issues.
I'd like to make an observation and follow it up with a question, if I may. And the observation first. Some years ago, in this very room, another speaker pointed out that where, in Germany, I think it was, where people had solar panels fitted, because they had an abundance of electricity, they started having air conditioning installed in their houses. So I say that in relation to demand reduction. The question then is, I think you mentioned early on about the perceived need, not your perceived, the perceived need for gas to provide more energy was because, was partly because of when wind couldn't provide the energy. But why is it that any wind turbines are turned off when the supply exceeds the demand of the grid? Why is there any wasted energy at all?
Okay, yeah. Yeah, I mean, the rebound effect you talked of, there is a rebound effect. And I think it's Jevons law, technically. You sort of create a better energy and people use more of it. And that's the effect you were talking about with solar panels in Germany. But unfortunately, that is something we have to address socially, really, and so on. But in terms of switching off the wind turbines at the moment, that is basically because we haven't got the energy storage to capture the excess energy, and the grid can't use it, so they can't overload the grid. So you've got situations in recent years where Scotland's had 100% on wind turbine energy because it's got a huge amount of offshore wind. In that situation, can they get that excess energy down to the south where we might be, we might have gas plants still running down in London or whatever, because we have much greater energy demand. So it's tying that up. And that's why there's so much being put on into these pylons, and upgrading the grid. You also need to upgrade the grid to take the renewable energy, because there's various aspects of the older types of energy which keep inertia in the grid. So we have to both put in pylons, energy storage, grid stuff, and that's all the stuff which is being worked on. Those boxes where I said electrons here, so that much, and by 2030 electron-based energy that much. There's a hell of a lot of stuff going on in the background to make that possible on the grid. It's not just, we have another offshore wind farm, but it's all the stuff in the grid, and it's really important stuff. My view is the government is doing really well in trying to push that forward. They're trying to push it forward as fast as they can go to do that. But that curtailment, I agree, is a real issue. It's something we've got to try to address this decade along with let's really get the long-duration energy storage going. There's long-duration energy storage in terms of pump hydro, quite a lot of it in Scotland recommended. There's one in Loch Ness, which I think is 2.4 gigawatts, perhaps, where it would extract water out of Loch Ness to a much higher reservoir up in the hills and then come down. Obviously, that's well placed because it's near all those offshore wind farms we're curtailing at the moment. But yeah, it's a real issue, but there are solutions to it, I think. Probably about looking at a decade before we get that really sorted, I'd say.
So you talked about electrons. The question is, how much effort is there being put into sort of pulling the stuff into chemical energy? Because I know the Orkneys have done that a lot in Scotland. No one has got more hydrogen they can cope with. The other thing with that, as I see it, is that the long-term balance for transport is going to be hydrogen based. So if you think about JCB and their hydrogen powered JCB digger. So is the government doing much on that front? Because the other one you can do is obviously the system that they brought in Iceland, where you take the CO2 and water, energy, methanol, you can then take that to dimethyl ether, which you can then liquefy, and that's a diesel fuel as well.
Yeah, I mean, there's a certain amount of research going on making fuels out of CO2, like you're talking about. On hydrogen's hugely complex area. In terms of production, there's lots of ways of making it, but there's blue and green hydrogen. And green hydrogen is also another way you could mop up those electrons offshore wind in Scotland and produce hydrogen and store energy in hydrogen. Hydrogen's basically an energy storage. It's not an energy source. And that is happening. I think things like the JCB diggers are to a certain extent fairly niche. And the issue is whether they'd be run off blue or green hydrogen, because blue hydrogen is the one which effectively on the analysis I've just given you is very, very dirty because of the upstream emissions. But it's where, electrolyzer hydrogen's much more expensive at the moment. And if you look at where you get a sort of tipping point towards green hydrogen, it's not till after 2040. So the risk is, in terms of climate issues, is you rush forward and put in blue hydrogen to meet demand for hydrogen rather than green hydrogen, which may be better. And you land up, locking in blue hydrogen out to the 2060s and so on. So again, I think that there's a debate there which is very nuanced, but one, from my perspective, one wants to steer it towards green hydrogen. One wants to steer it towards hydrogen where it's best used. And there's something Michael Lebrecht, who's an energy expert, worth listening to him. He's different views to me, but I listen to him a lot. He's really good analysis. He's done something called the hydrogen ladder, from sort of best to worst. And I think things like truck hydrogen may be sort of up at about 2 or 3, that yes, it's worthwhile. Things like hydrogen cars are sort of right down at 6, don't bother with hydrogen cars. Electric cars are much better. And, it's just a waste of making hydrogen to burn it again in that sense. And actually it's a waste to burn it again in power stations, which is something coming up, as James and myself know. They talk about co-firing natural gas and hydrogen. There's a massive amount of hydrogen, but you take 3 green electrons from a wind farm in Scotland or somewhere, and you output 1 dirty electron at the end of the day because you've turned it into hydrogen, turned it back and put it through a power plant and all the rest of it. And if you do the analysis, you're throwing 3 nice green electrons into 1 dirty one. So yeah, it's a hugely complicated subject, but there is a role for hydrogen, but I think it's much less than a lot of the hype.
Thanks for such a good talk, Andrew. Could you say something about the international implications of UK policy? Because I think there's 2. I think the UK looks very pleased with itself in an international context, and there's little justification for that. Of course, we've had a massive success with renewables in electricity generation, but 2 things. First, there's the way that our budgets are set, and there's been critique of that from the Tyndall Centre a lot in the headline, which is a factor of 2
or 3,
or 3. The scientists there say that the budgets just are not right given the UK's historical emissions. But I think relevant to what you've been talking about, a second issue is the technological focus on CCS is immensely damaging in a world where coal is still going up. and gas is still going up.
Yeah.
That may not be happening in the UK, but that's what's happening in the world, and with the international energy corporations. And I mean, to me, it was summed up by the memorandum between the UK and Saudi Arabia in December 2024, where the UK is talking about supporting the development of CCS in Saudi Arabia, which is a country which desperately wants to continue producing fossil fuels for the indefinite future when they should be reducing very fast.
Yeah, absolutely. Thank you, Simon. Yeah, I mean, I've sort of veered away from talking about carbon budgets and so on because they're quite complicated. But I think some things to say about that is that we hear a lot about the UK climate policy and we hear a lot about carbon budgets. The first thing to say is that they're enacted through the Climate Change Act in 2008. And the Climate Change Act effectively, it actually set up a very good mechanism. There's lots of things I like about the Climate Change Act, I should say. It set up what I'd call a sort of well-tempered synthesizer. In the, if you know the quote there, or well-tempered organ, or the Bach quote, but but what it does is it basically only looks at UK territorial emissions, and it just measures what we're doing in the UK economy. Initially, it didn't look at aviation and shipping, and in fact, they're only coming in 2028, but they're legislated to come in now and so on. And the problem with CCS, to start with the problem with CCS, is that the picture with, you know, the 2/3 of the emissions are out over the Atlantic if you're using LNG, to start with. And then even if you do the carbon capture, you then have 95% of the emissions from that piece of infrastructure out over the Atlantic. The UK government and the Climate Change Committee basically are taking sort of, oh, well, that's out there. Well, we've got this very good system which works for our UK emissions. And, you know, aspects of it are good. And they basically don't bring that into the policy. So one of the things a number of us are trying to do, and I know you are very much, Simon, is trying to raise that. Now, we can't actually say, well, we've got it wrong, you know, because carbon budget's wrong, because the carbon budget's worked out by this calculation which externalizes our impacts internationally. But what we can do is keep raising that in various ways. And we're doing that. But there is another issue for carbon capture in the carbon budgets that, and this has come out of, there's been 2 legal cases on the plans which go with the carbon budgets. One was called the Net Zero Strategy, one was called the Carbon Budget Delivery Plan. And both of them said to the government, you've got to go back and do the plan. And they've just released the 3rd plan last autumn, actually. But one of the key things which came out of that is this fact, basically to do with uncertainty and risk, that when the Committee on Climate Change advised the government, this is what you need to set for the carbon budget, the amount of carbon you can do in this 5-year period. That's what that means, by the way. They basically just added up all the emission savings they thought would get, the absolute emission values with no risk assessment. So they basically said everything is 100% likely to work. So, you know, we'll do this thing of introducing heat pumps. Oh, that's 100% work, and that will get rid of 5 megatons of carbon out of the system or something like that. That's the sort of logic. Well, what the legal case established was that they couldn't do that. They actually had to sort of say, well, actually, maybe that policy will only work 70% and deliver 70% of that 5 million tonnes. So as a result of that, you've got risk analysis effectively has legislated through litigation has to be done in the carbon budgets and the carbon plans to deliver those budgets. Well, carbon capture and storage, I've given you a large presentation of all the risks which aren't actually being calculated. And the assumptions which are going into the Committee on Climate Change advice for the 7th carbon budget are things like it will do 90 to 95% capture. They're not including anything to do with the methane impacts. They're not including things like whether the storage will work and whether there's impacts from that. So what you've got there is a risk factor to setting the carbon budget, which hasn't actually been sort of acknowledged publicly or in the public process yet. So that is very much one way that carbon capture and storage, I believe in the fairly near future, may affect legal responses to the setting of the 7th carbon budget, advice given on the 7th carbon budget, and so on. Did I answer your question, Simon, by the way? Because I may have gone off somewhere else, I think. But was that...
You talked about carbon budgets.
Yes.
I think it's generally... I think presenting this technology as one of the answers to climate change is terribly dangerous.
Yeah. The only other thing I'd say on that, because this is an even a bigger example, actually, I've talked a bit about BECCS. BECCS is bioenergy of carbon capture and storage. In the climate plan, the UK is saying, right, we know we're going to have something, I can't remember the exact number, something like 30 million tonnes of aviation emissions, which they now have to account for after 2028, going out to 2050 per year. And, how do we get to net zero in 2050? Right, we've got 30 million tonnes of aviation still there in the system. The main mechanism they're using for that, and they're also using it for some agricultural emissions, actually, is, we will do this thing called BECCS, and it will... I haven't explained that they say BECCS is a net negative energy technology, in that not only will it save some emissions, but it will... it's complicated. This is where I say the accounting's not right, but they actually say it will create negative emissions in an overall mathematical analysis. It's actually extremely flawed, and it's got assumptions which are completely sort of unjustifiable. We talk a lot about that in the bar, if you like. So they're saying, we'll do these negative emissions. We'll get sort of something like 30 million tonnes of negative emissions to offset our aviation, and it will all be hunky-dory on the left. And that's the sort of thing, Simon, which is hugely, hugely alarming. Actually, it's hugely, hugely alarming from a scientific mind in terms of some of the thinking going on in Whitehall about these issues.
There's loads of loads of questions, which is absolutely brilliant. Can we, for the physical audience here, save those for the networking session? But there's one question from the... Sorry?
I don't need electricity.
I'm speaking to... Oh, I thought I was sorry, really loud. No, can
We're a species, as you know, all of you know, that's become totally dependent on the use of fire for our survival. We've lost our bodily hair through evolution, so we need to protect ourselves with warm clothing and to grow our food in the farms. And we are herbivores, if you evolve from herbivores, if you look at our teeth. So we just need really vegetables. And the final question, why the hell do we cook our food when you can just eat green, lovely vegetables?
Well, a good point. And, raw veg diet, I think, is pretty good for some things. But But we should be able to do our cooking, with electrons.
Can we have Can I
Oh, yes.
question now? So if Steve relates an online question, and can all the rest of the questions be addressed during the network session after this, please?
Yep, so we've got quite a large audience online, and maybe a couple of questions from them.
Thank you.
Yep. So the first one is from Rob Palgrave. Are there any large-scale, greater than 500 megawatt gas power stations with CCS operating dispatchably and reliably anywhere in the world? If not, isn't it the case, therefore, that UK policy is based on FOAK?
Yeah, first of a kind, that means. I think the question was, are there any gas-fired power stations with CCS anywhere in the world? No, the one I showed on the map, Net Zero Teesside, is the first one which is being developed in the world. And that one, is very much first of a kind. It's not even clear. Actually, I was talking about the storage risks earlier. Irrespective of the technology and the greenhouse gas emissions and so on, or the technology of the power station, it's not even clear that that storage site will be able to take as much CO2 as they've projected, actually, for the whole, at least for the whole cluster. There's papers which suggest that it's sort of limited to a certain rate of CO2 going down the pipe and beyond that. But I draw you back to that Norwegian example where they, it's had 18 years of storage capacity and it stopped working after 18 months for various technical reasons.
Store turbine energy by gravity.
Gravity energy is quite a good one, actually. Yeah. Reusing coal mines and things with weights.
So one more right at the end. Current CCS is currently assessed as essential to meeting UK net zero plans. So what would you advocate should replace it in the net zero plans? That was from Anne-Marie Williamson, partially answered by Rob Palgrave, talking about driving emissions reductions quicker, etc.
Okay, yeah. That comes back to what I was talking about after Simon's question, really. That, yes, it is factored in to the climate plans and the advice to the government, a certain amount of it. It's actually, I believe it's less than 5% of the total emission savings needed. As I've said, if it's gas-fired power stations, it's not even making emissions savings in the round, but they will claim the emission saving from the capturing for UK carbon budgets and forget that they're trashing everything internationally. So what do you do about that bit? As I said, it's not been risk assessed too. Well, that's where the government actually need to look at the climate plan again, actually, and they need to draw in, there are other measures. There's always other measures. The climate plans and the advice and committee on climate change are drawn up on balancing a number of things. For example, you could take a much tougher line on transport, and I myself have worked on that, but the transport sector, basically, the transport sector emissions have not gone down, even though we're introducing lots of electric vehicles. They have not gone down. They're stuck at around something over 100 million tonnes of carbon a year. And that is exactly one area that you could cut much more radically with more radical policy, which means you don't have to rely on carbon capture. I want to come back, actually. Simon asked me, I realise, Simon, you asked me about setting the budget overall, and this is very relevant on this, that when you look at it is an important point, when you look at the global carbon budget, and this is worked out by the IPCC and everything, and it's absolutely, solid science. We know more or less how much carbon budget we've got. There's statistical variation on it, but we know all that. And when you look at that, the UK is using 3 times as much as its fair share. And under the Paris Agreement, there is a sort of Article 4, I think, basically says, it should be fair share amongst nations. There's various interpretations of what fair share means, unfortunately, which will be legally litigated, I think, over the years to come. But the UK, given climate analysis by scientists in Manchester and the Tyndall Centre, so we're using 3 times as much. So the problem is with the question from Anne-Marie Williams is not just what do we do about the that carbon capture bit, which we need to find something else to deliver those emission cuts. But really, we need to go right back and renew our carbon budgets right from scratch. And it's also something else I'm working on in various ways, and others are too, actually. As I said, the Climate Change Act was brilliant in its day. It's been there for 18 years, and it's now getting outdated, and we need a complete revamp of that.
Brilliant. Let's close it at that. All future questions, please, can you address during our networking session, which we have to have now.
Okay, and that's in the bar, I think.
In the bar, over a glass of wine. Andy, thank you very much.
Oh, thank you.
Talk. Excellent. And just to finish off, we've heard a lot of positive spin about carbon capture, but we need a good balanced argument and a critical look at the facts, and that's what you've been doing. So, brilliant. Thank you.
Thank you. Thank you, everybody, for sitting through all that as well. I appreciate you sat through longer than you thought you were coming for.